Alright guys, we are back with, I think this is the third video that we're going to cover in Chapter 7. This one actually takes a little bit of a tangent. This information is actually from like in a chapter in the 30s about plants, somewhere in there. If you went and looked at like page 740, we'd start to get information about what we're going to talk about today. But the kicker is that one of our first labs that we're going to do actually pertains to understanding this particular idea, which is known as water potential. Okay, and we talked last video. The last thing we discussed was this phenomenon known as osmosis, which is nothing more than the movement of water or the diffusion of water. Okay, across a semi-permeable membrane, either in a plant or an animal or wherever. Okay, and so we kind of learned about it in a qualitative way, right? We looked at this kind of U-shaped tube, and we looked at the amount of solute that was in one side versus the other side, and we decided, okay, water is going to move in a certain direction. Scientists have taken to actually quantifying this a little bit in this this measurement called water potential. Okay, so as we mentioned before, osmosis does determine the net uptake or water loss by a cell. And osmosis is affected by the solute concentration, but it's also affected by the physical pressure on a system. And that is something that water potential takes into account. Okay, so water potential is a measurement that combines the effects of the amount of solute, but also the amount of pressure on a system. Okay, so it takes into account both of these things, where, as in those qualitative examples we saw in the last video, just kind of looked at the amount of solute potential, the amount of solute concentration that was there. Okay, water potential. Once we figure out the numbers associated with a certain solution or a certain system, the number of that we obtain for the water potential can determine the direction of the movement of water. And this comes this final statement that we see right here. Let's see if I can get the pointer up. This final statement that we see right here in this slide refers back to one of the slides that we talked about in the previous video, in video number 2. Water flows from regions of higher water potential to regions of lower water potential. And what this means is that we're going to calculate the water potential of possibly two different environments. An environment where a cell might sit in some kind of like a beaker or something, and then the solution that's in the beaker itself. So we can calculate the water potential of the solution inside of the cell, but also the water potential of the solution outside of the cell or in the beaker. Okay, and so when we get these numbers, when we ultimately calculate these numbers, we will find that one of them is generally higher. Okay, sometimes they're the same, but generally one of them will be higher than the other. And basically what that tells us is that the number that is higher, the environment that has the higher water potential number actually has a higher concentration of water molecules. That's essentially what it's telling us. Okay, and so we would take that onto account, and we'd say, okay, water is going to move from an area that's got a higher water potential to this area over here, which might be a lower water potential in terms of numbers. So how do we calculate those numbers? What goes into the calculation of those numbers? In fact, it is two different things, and just mentioned them on the previous slide. The water potential is a function of what is known as the solute potential and also the pressure potential. Okay, so I'm gonna flip my computer here so I can draw on it. Kind of looks awkward, but that'll work. All right, so I'm gonna make a writable copy of this slide that you might be looking at right now. And I'm going to write the equation for water potential on this slide. Okay, so I want you to write this down either in your notes or however you happen to take notes, or just make special attention that this part of the video has something relatively important on it. This symbol right here stands for water potential. Okay? Water potential is a function of the solute potential plus the pressure potential. Okay? So this symbol stands for solute potential. and this symbol stands for pressure potential. Okay? So, you might be asking, how do we calculate this stuff? What goes into the calculation of these numbers? What do we got to plug into these symbols? Are we measuring something? That's what we're going to talk about right now, okay? So what I want to talk about first, I'll get the eraser here. All right, what I want to talk about first is the pressure potential. Under normal atmospheric conditions at sea level, there is like a default mode for pressure potential. Most often, and this will work great for normal, right? Because normal is almost right at sea level. It might be a little bit above sea level. So we are at normal sea level. We have relatively normal atmospheric pressure. At those kind of stock conditions, those conditions that are what we would consider to be normal scientifically, scientists have verified and said that we're just going to make pressure potential 0 under these normal conditions, okay? So when we're at sea level, when we are at room temperature, and when we have normal atmospheric pressure, maybe there's no storms or anything coming through or hurricanes or whatever it is, then the pressure potential, the number 4 pressure potential, is going to be 0, okay? Now, if we lived in Denver, Colorado, we might have to change this. And there is a way to calculate it. We're not going to worry about it since it's going to make things harder, okay? In the problems that we get or the problems that we see, they will either give you the pressure potential, you will either get it, or you will assume that it's 0 if they don't tell you anything about it, okay? So do keep that in mind when we look at that. So that's an easy one, right? That's an easy one to just kind of say, okay, we've got it, we've figured it out. And it's one more thing off our plate that we don't have to worry about, okay? Let's then talk about the solute potentials, because the solute potential is the one that's going to cause people some issues, okay? I'm not done erasing there. All right, solute potential is going to be a little bit more difficult because we actually have to do some kind of calculation. And so there is actually another equation that we can plug numbers into that associates with the solute potential. And it is this, negative I CRT. Okay? Now, each one of these letters corresponds to generally either something that we know, maybe it's a constant, or something that we can figure out, find, or measure. Okay? So let's start off to the right side here, the easy stuff. Okay? T stands for, I bet you can guess, temperature. Okay? And when we're doing problems with these, the temperature needs to be in Kelvin. Okay? Because we're scientists. That's what we kind of default to as the scientist. R might sound like, well, what does R stand for? R is something you might have heard before in in chemistry, right? R is a gas constant, and it is of value 0.0831. Okay, 0.0831. So we can just plug that number in there, so we can figure out the temperature in Kelvin of a system just to use a thermometer. We know R. Okay, easy stuff, right? Let's go to C. C is the I'm going to make the arrow bigger. The solute concentration. Okay, the solute concentration of the system we happen to be looking at. Okay, now sometimes this has to be figured out. Sometimes we know because we've mixed it. In the lab, one of the labs that we do, what we're going to have to ultimately do is figure this out. We would not know this, so we have to actually figure it out. Okay, and then I stands for the ionization constant. Okay, and the ionization constant tells us how many ions a particular substance might happen to break into when it becomes mixed with water. Okay, so for instance, one of the common ones that we're going to see a lot of is sucrose. Sucrose actually does not ionize, so it breaks into one molecule, which is still sucrose, all right? So the ionization constant of sucrose would be 1. I'm going to ask you a quick question. You can pause the video and try to answer it. What would the ionization constant be of salt, NaCl? Okay, if you answered 2, you were right. It breaks up into the ions Na plus and Cl minus. So the ionization constant of salt is 2. So for every different substance, there is a specific known ionization constant. And if you don't know it, then you can just look it up, okay? So a majority of the things that we see in this equation to figure out solute potential can be either gotten really, really easily through simple measurement, like the temperature is already known, like the ionization constant and the gas law constant. And some things like the solute concentration might be a little bit more difficult to ascertain, okay? And they will be, at least in our lab when we do it, okay? So I'm going to erase all this. Hopefully you got that. It's on video. If you didn't, you can go back. That's the wonder and the beauty of video. All right, it just takes forever to erase. All right. All right, so when we ultimately figure out what is the solute potential, we can add it to whatever the pressure potential might be, and that gives us our value of the water potential, okay? So by looking at this, we can understand that the water potential, okay, the ultimate number that we are going to try and ascertain is a function of how much solute is in a specific substance, and also the amount of physical pressure on a solution. And that can be done in many different ways, which we will see in these examples here, okay? Now, let's walk through. We're going to walk. I think there's 3 examples here that kind of walk us through this YouTube example, like we saw in the previous slides in the previous video. But it incorporates this idea of water potential. Okay, so if we look at this scenario, let's break it down little by little. Right? Let's look at what will happen if we take some solute and we put it into one side of the water, into the water column, okay? In the middle here, we have the selectively permeable membrane. The only thing allowed to go through this selectively permeable membrane is going to be water, okay? On one side of this tube, on one side of this tube, we have pure water. On the other side of this tube, we have some stuff in there. We don't really know what it is. It's purple stuff, okay? And that purple stuff is at a concentration of 0.1 molar. Okay? That's all we really need to know about it. It doesn't give us a whole lot of stuff. And in fact, they're going to use just arbitrary made-up numbers to help us kind of understand and realize what this is. So these numbers that you see are not figured out. They're nothing that actually you have to worry about. Where did they get that number? Why is it that number? You don't have to worry about it. They've picked arbitrary numbers for this. Okay. So let's break it down side by side. Let's look at how they figured out the water potential for pure water. Okay, for pure water, let's take all of the stuff into account. I'm going to make a copy of this here. For pure water, let's figure out what is. We know that the water potential is 0. It says the water potential is 0. Okay, at the bottom here. But we know that water potential is a function of the solute potential and also a function of the pressure potential, right? But it doesn't say anything about either one of those two things, right? But what do we know about the solute potential? What has to be in the solution to change the number for this? What has to be in the solution to change the number for solute potential? If you answered solute, you were right. So if there is no solute in a water sample, the solute potential is 0. You have to have solute in something to decrease, right? Because if we think about what solute potential is, there's a negative here. Okay? That kind of got lost. Negative ICRT is used to figure out solute potential. So if you have any solute in there whatsoever, the value of the solute potential is going to be negative. If it's 0, that means there's no solute in there, okay? And we can assume, since they don't really say anything, we can assume that the pressure potential is 0. And so that tells us a little bit about this system, in that this experiment that you see on the screen right here is probably taking place in the lab here at school. Okay, it's at sea level, it's on a beautiful day like today, it's at room temperature, and there's no pressure systems coming in because of weather. Okay, so when all of that stuff is in play, the water potential of pure water with all those caveats filled is 0. Distilled pure water is 0. Okay, so let's get that out of the way, because those are assumptions that you'll also have to make when you hear the terms pure water and water potential. Always think of 0. Okay, now let's look at the other side here. This side has stuff in it, right? There's stuff in here. The solute is dissolved in this side. So before we even look at this, these numbers, you can avert your eyes from those numbers for a second and think to yourself, what is this system as a whole going to look like numerically, right? Let's look at the, I'm closing my eyes. Let's look at the solute potential, just kind of big picture. The solute potential, we know, has to be negative because there's solute in it, right? It doesn't necessarily matter how much is in there. Okay, that'll come into play later. But we know that there is going to be a solute potential, and it is going to be negative because there is solute in this system. Okay? We have to get that out of the way first and foremost. The other assumption we can make is that this side of the system right here is also at sea level because it's connected to this side, which we've established was at sea level and under normal conditions. So the pressure potential is going to be 0. Okay? Keep that in mind because all of those things are normal. And they've included this arbitrary number of negative 0.23 for the solute potential. And it is that negative number because there is solute in that side. That's all you have to worry about in terms of how these numbers play out. Okay, so let's then calculate the water potential. Remember, water potential is this right here. Water potential is that. So we add these two numbers up. Hey, lo and behold, we get a negative 0.23. That makes sense, right? So now we've got two values for water potential. We've got water potential for this side of the system, which is right here. And we've got the water potential for this side of the system, right here, which is here. Okay? Now we can compare those two terms. We can compare those two figures. Now if I go back a couple, we've got a statement here that tells us how water will flow. Water flows from regions of higher water potential to regions of lower water potential. So let's apply that statement. We've got a water potential here that is 0. I'm going to go back to my, I don't want to do that. Yes, I do. Let's go back to this guy. We've got a water potential here that is 0. We've got a water potential here that is negative 0.23. Let's compare them. Which one's higher? I know this has a value, right? This is a value of 0.23, but it's also negative. So 0 is technically higher. So that's why we see this arrow right here moving from left to right, because this area right here has a higher water potential than this area here, which has a lower water potential. 0 is higher than negative 0.23, so water will move from here over to this side. Okay? Another way we can think about that qualitatively is to say that this water wants to dilute this solute. Makes sense? Remember all those descriptions of how water will move? They apply here as well. Okay, let's move on to the next example. So in this example, all we did was we put some solute in there. Okay? Now we're going to play around with the other value. Okay, the other value being physical pressure on a system, and we see that happening right here. So let's look at this side. This side's easy to look at. Okay, this side's easy to look at because it's still the water potential of 0. Okay, so that still tells us that we have pure water here with nothing dissolved in it. Pure water, nothing dissolved in it. But this side here, what does this number tell us? Pause the video and see if you can't think about what does that number tell us about this side of the system here. All right, if you said that it tells us that the exact same amount of solute is dissolved as was in the previous example, you were right. Or if you said something about that. Okay, number one, it tells us that there is solute dissolved in here, number one. And number two, it tells us that the exact amount of solute that was dissolved in the previous example is dissolved here. Okay, because it's the exact same value. Now for this example, what they've done is they've taken this piston. Okay, we see this piston right here. It's colored in red. And they've taken this piston and they've put physical pressure down. They've increased or applied positive pressure onto this side of the system. Okay? And so that is represented here by this arbitrary value. It just so happens that they picked the number positive 0.23. And the reason it's positive is because we're putting positive pressure on this thing. Okay, when you push down on this tube system with that piston, you're putting positive pressure on there. Okay, so now again, let's take into account what water potential tells us. It tells us that it is a function of the solute potential plus the pressure potential, right? So we add these two figures together, and they turn out to be 0. Okay, so then let's figure out which way water will move. Which way is water going to move? Well, in isotonic situations, water will move back and forth, back and forth, back and forth, back and forth. Okay? This system is technically at equilibrium, and it is at equilibrium because we have put physical pressure on this system. Yes, initially water will move from this side over here. Okay? That's assuming that this side here was at a higher level. But once it gets to this level here where these numbers are all equal, water will just move back and forth and back and forth and back and forth. So there is no net movement of water. Water just continues to go back and forth, and that makes sense. If there's isotonic conditions, if the water potential here is the same as it is here, then water's not going to really move anywhere. Water's not going to move anywhere. Okay, not any net movement anyway. Okay, so that's an example of what physical positive pressure will do to a system. Let's look at the next one. The next one increases the physical pressure even more. Okay, now I don't think I really need to write on this one. It's just an extension of what the previous example was. But we see here that we've taken and applied even more pressure to this piston right here because of two reasons. We look at the pressure potential. It's increased from positive 0.23 to positive 0.30. Okay, so that tells us we're pushing down with even more pressure than the previous example. The solute concentration is still the same. Okay, when we're trying to figure out water potential, we add these two numbers together. We get a number of 0.07, positive 0.07. So how does water move in this system? Water moves from the area of higher water potential to the area of lower water potential. Okay? So in this case, we've got water moving from this right side to this left side. This area, 0.07, is a bigger number than this number over on this side, which is 0. Okay? So as a result, water is going to move from this side to this side. It's kind of easy. Now, in this instance, we have to describe the water movement based on water potential, because if we go back to some of our other examples or other descriptive ways of how water moves, they don't float. They don't, no pun intended there, they don't work right. Okay? So in this case, water does not dilute the solute. Okay, because water is moving actually away from the solute, but the reason for that is because we have to take into account the physical pressure on that system. Okay, all right. Last example here with water potential has us apply negative pressure. Okay, this is the same phenomenon that you would get if you sucked up on a straw. Okay, you are applying negative pressure with your mouth. Okay, on the straw, and you know what happens then. You do that so you can get a drink of the water or the pop or whatever the heck it is, right? And so in this case, if you have an airtight seal here with this piston and you pull up on it, the exact same thing is going to happen as if you were sucking on a straw with your mouth. Okay. So in this case, we're applying negative pressure. So now we're going to mess with this side. So I am going to take a snapshot of this one here so that we can play around with it. Let's break down this side first. This side here, it still has the exact same amount of solute. Okay, but now the pressure potential is 0 because we've stopped screwing around with it. There's no more piston in there. Atmospheric pressure is just normal. Okay. So the solute potential is still the same, negative 0.23. We can look and add these two together, okay, to get the overall water potential is negative 0.23. Okay. Now we look at this side. We still have pure water, pure H2O, pure water, which makes our solute potential 0. It's still 0. Okay. But the thing that has changed is that we have now decreased the pressure at the top of this system by pulling up on this plunger. Okay? When we pull up on this plunger, it produces a pressure potential of negative 0.3. Okay, so we add those two figures together, negative 0.3 plus 0, and we get an overall water potential of negative 0.3. Okay, so let's do some comparing now. We want to figure out, ultimate goal here is to figure out how water is going to move, which way is going to water move, and we want to be able to describe it using some of our terminologies. Okay, so we can say here water will move from the right, okay, the right to the left, because this number of water potential is higher than this number of water potential. Okay? So yes, they're both negative numbers, but negative 23 is a bigger number than negative 0.30. That's exactly what water does. You see the water rising on this side. Okay? So in this example, water is moving from this area of greater water potential to this area of lesser water potential. Okay? I hope that this explanation and drawing all over these beautiful diagrams helps to explain what water potential can tell us about how water moves across selectively permeable membranes. That is my hope. Now, I also understand that this is a relatively difficult concept. Okay, so I want you to come back with questions. I want you to jot things down that you just didn't understand, something you want me to go more in depth with. Okay, please bring those questions to me. All right. So let's apply this now to living systems, okay? There are two different scenarios here, right? So in the previous examples, those were just idealized experimental tubes that are full of water and solute, and we can use plungers on them, right? They're not living systems. But, you know, the reason we're studying biology is because we want to know how some of this stuff interacts with life, right? And I know plant life is generally considered boring, but we're going to use plants in this example here, all right? So in this diagram, shoot, you know what? I'm going to wait until we have a live session for this. Yeah. What do I want to do? Yeah, let's go ahead. We'll wait for a live session on this picture. Okay, I'm going to ask you questions about this picture right here. So I'm going to continue on and talk about this picture right here. Okay, so we do want to have, you know what, never mind. I'm going to go ahead and do this. I'll edit that out later if I feel the need to. I will do this because I think that the water potential stuff is difficult enough where you might not really know what you're going through unless I can be there to walk you through it at that time. So let's break this picture down here. We've got a beaker. Okay, I'm going to make this guy here. We've got a beaker. This beaker right here is full of a solution. Okay? It is full of a solution, and this solution is described right here. It's a 0.4 molar sucrose solution. So one thing we can make sure that we understand about this is that this water in here has sugar in it. Okay? So that can tell us something about the water potential right off the bat. Okay? It can tell us that the water potential is not going to be 0. And it can tell us also that the water potential is going to be negative. It has to be negative because this solution has stuff dissolved in it that we just obviously can't see, but we know it because it's described here. Okay. The other thing we can gather by looking at this equation is that this experiment is taking place here in the lab, okay, at Normal Community. And we know that because the pressure potential is 0, which is normal atmospheric conditions and temperature and everything else. Okay. So what we're going to do with this experiment is we're going to take a cell, okay, specifically what is called a flaccid cell. Okay, a flaccid plant cell is basically one that needs to have some water. Okay, it's not a happy cell. It's just kind of there. It's kind of it's kind of blah in life. That's the way this flaccid cell kind of goes through life. It's like meh. It's not happy. It's not super sad and dead. It's just kind of like right in the middle and blah. And so that's how you could classify a flaccid cell. It wants to be watered. Really is what it needs, okay? And so this cell is described to us up here, okay, with these numbers right here. And so these numbers tell us, again, something about this cell. Number one, that it is the same, it's taking place in the same laboratory here at Normal Community because the pressure potential is 0. And also that it has some stuff dissolved in it. It has a solute potential, so that means there's stuff dissolved in here. If this was class, I would ask you, hey, what is dissolved in here? And you would tell me all sorts of stuff, including sucrose and starch and blah, 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 all this stuff. So the solute potential in this case is actually a function of all the stuff that is dissolved in this particular cell, okay? And it comes out to a value of negative 0.7. Now, the next question I would pose to you, and maybe you want to pause it and answer it here, is which way is water going to move? Is water going to move into or out of the cell based on what we see here with our figures? So to answer that question, you would want to look at the water potentials of the solution and also the cell and then compare the two. And so then you would say, if you got this question right, you would say water would move from the cell into the beaker. And why would I say that? Well, number one, you can see the little blue arrows here. That's how all the kids cheat in class last year. You can see the little arrows. Those arrows indicate the movement of water. Okay, so use your resources if they're there, I guess. But in terms of how we've described water's movement, especially as it relates to water potential, we would say water moves from areas which have a higher water potential. Okay, negative 0.7 is higher than negative 0.9. So areas of higher water potential to areas of lower water potential, which is where we see the water moving. It moves out of the cell. Okay, and this actually creates a situation known as plasmolysis. Okay, plasmolysis is when the inside of a plant cell like shrivels up and the cytoplasm rips away from the cell wall. It's really, really bad for the cell. It could kill it, in fact. Okay? So that's exactly what we see here. We have put this plant cell in an unhappier situation than it already was. It was already kind of blah to begin with. But in this case, we've made it basically die. Okay? We've sucked any remaining water out of it and put it into the solution. Because, remember, if there's more solute in this one, which it looks like there is because the solute concentration is greater here than it is here, water from the cell is going to want to dilute the solute. Okay? So all we've done is quantify that terminology, if that makes sense to what we're doing. Okay? The bottom scenario, okay, is using the same exact cell, which we see up here. It's the exact same cell. It's unhappy. It's blah. And this one here, this solution is what has changed. Okay? Instead of putting the flaccid cell into a sugar solution, we're going to put that cell into distilled water. Okay? And distilled water is easy, right? The distilled water water potential is 0. So I'll ask you the same question again. which way is water going to move? Is it going to move into the cell or out of the cell? And you would spend some time and you would think to yourself, oh, okay, what's the water potential? The water potential of each system. The water potential of the distilled water is 0. Okay, good. The water potential is 0. The water potential of the flaccid cell is negative 0.7. All right, which one's higher? 0 is higher than negative 0.7. So water is going to move into the cell. Water will move from areas of higher water potential, okay, to areas of lower water potential. Okay, so it's going to move from here in the distilled water where it's high to in here where it's low. Okay, so that's why it's good to feed plants water, distilled water. You don't want to feed them sugar water. You're not doing them a favor. You're not giving them like a boost. You're actually sucking the water out of them. So just feed them distilled water and they'd be happy. And that creates a situation here called turgidity. Okay, and that term has been mentioned before when we talked about central vacuoles. We are filling up this plant cell's central vacuole with water, and it actually causes the cell to be kind of like, meh, it's kind of gross and limp and flaccid, and then it kind of goes, and it puffs up real good, okay? And so that causes the plant to actually stand up. And you can do this at home. Deprive some of your house plants of water for 3, 4, 5 days. Don't feed them water, and they'll start to wilt on you. And then pour a bunch of distilled water in there and go back in a couple hours and see what it looks like. You could take before and after. You could do time lapse, and you see that plant puff up. And the reason for that is because all of the cells in that plant have taken on enough water where their cells can actually push against each other and they actually stand up. It's kind of a neat phenomenon. Okay, and we see it a lot in our garden over the summertime. All right, so I'm glad I did that. If you want to ask any questions about that during any live sessions, we can do that as well. Okay, so water balance in cells is important, and I don't want you to forget about these terms that you see in front of you: hypertonic solutions, isotonic solutions, and hypotonic solutions. They are just as useful as understanding the more quantitative water potential to describe each one of the systems. Okay. And so one thing I do want to just briefly hit on here is the fact that depending on what you might be looking at, whether it's an animal cell or a plant cell, different types of solutions can be beneficial to some but detrimental to others, okay? So if we look at this example here, okay, we have taken, I'm going to snapshot this bad boy again too. We have taken a couple of examples here of cells and put them into certain solutions. So this surrounding liquid here that you see in blue, okay, all this stuff here that you see in blue, is described as, I don't want the ruler, is described as a hypertonic solution, okay? And so what that should tell you is that just macro scale, that this solution has more solute than this cell, okay, which has less solute. Remember, when we use these terms, they are in relation to something else, and the thing that they're in relation to in this picture is the cell, okay? And the same thing with the plant cell. There's less solute in here. Now, let's think about how water moves, just qualitatively, okay? Water likes to dilute the solute, okay? So in the animal cell, water is going to leave the cell and try and dilute this greater amount of solute, this higher concentration of solute. Same thing with the plant cell. And this actually leads to something known as plasmolysis, which I mentioned in the previous slide for the plant, and just causes a shriveled cell here in the animals. Okay. Now, both of these are really, really bad. Both of these scenarios are really, really bad for either plant or animal. Both could theoretically lead to organismal death unless water is added. Okay, so this can be really, really bad. It's one of the reasons you don't drink salt water. Okay. Now, if we place these things in isotonic solutions, let's place both plant and animal cells in isotonic solutions. That means that the solute is equal. There's equal amounts of solute inside and outside of the cell. Okay, so for animal cells, we've got an equal exchange of water into and out of the cell, and this is normal. Our cells as animals really like this particular scenario. Plants, on the other hand, don't. Okay, plants, this leads to the flaccid state of plant cells, which kind of makes them like, they look like they need to be watered. They're starting to get wilty. And so this is an indicator of a downfall of the plant, a quick downfall of the plant. You still have water out and water in, but because of the nature of plant cells, they want a lot of water. They want to be full of water, okay? So generally speaking, this is kind of baddish for plant cells and goodish for animal cells. All right? So let's look at the last situation, which is a hypotonic solution. The hypotonic solution has less solute than the other system, which is the cell. And so we want to figure out which way water is going to move. Water likes to dilute the solute, right? So in this scenario, water will seep into the cell, okay? Because it will go from this area has lower concentrations of stuff to this area that has higher concentrations of stuff. Now, in this instance, this leads to animal cell lysing, and that is bad. Okay? This is a scenario that will destroy cells. In fact, there are certain immune system responses that lead that destroy infected cells by this means. Okay, so it can quell the infection quickly. So this is bad for cells. It'll kill cells. Okay, at least for animals. Now, the same thing happens with plant cells. They will have this water move from areas of higher concentration, of lower concentration of solute to higher concentration of solute. Okay, so water will follow the solute or dilute the solute. And what that causes is a normal state for plants. This is a good state. This is that turgid state that we showed in the previous slide. Okay, so it's just, I like to show this because of the kind of dual nature of, you know, what animals and plants like in terms of how much water their cells will actually take in, and what kind of solutions are good to give these particular animals, okay, or plants in some cases, right? So let's kind of move on here. Since we are on the topic of living things, I want to talk just, you know what, we've been doing this one for a good half hour. I'm going to go ahead and leave this talk for the final video, okay? And it'll be a good kind of transition. It'll be a good time for us to go over a review of some of the stuff we covered in the previous two videos, okay? So I will be back with a fourth video shortly, and you guys have a good day.